So now that you know how to solve different separable differential equations, you have a tool that you can use to derive the exponential growth equation. You use the exponential growth equation in advanced algebra. It's the one that's sometimes called PERT. So we're going to go through the process of deriving that equation. So there's a special kind of differential equation, which is a constant times y. And I'm going to show you the process for solving this differential equation. It's the same as what we were doing in the last section, except we're not going to solve c until the end. We'll do that as the very last step. So I'm going to move the y's over. So I have dy over y equals 3 dx. I'm going to do the antiderivative, so that's natural log of the absolute value of y equals 3x plus c. I'm going to exponentiate, so I have the absolute value of y is equal to e to the 3x plus c. And then I'm going to write that as using the exponent rule for multiplication. I'm going to write that as 3 to the x times e to the c. And so the absolute value of y is equal to that. I'm going to write that as y is equal to plus or minus e to the c times e to the 3x. And now this whole thing is some constant. I don't know what the constant is, but it's some constant depending on what c is. I don't really care what c is. I just want to be able to write this equation. So I'm going to call this constant p. So I have y equals p times e to the 3x. Now if I have an initial condition, and my initial condition is 0, negative 8, if I plug in 0 for x, I have negative 8 is equal to p times 1, so p is equal to negative 8. And so this is my function, y is equal to negative 8 e to the 3x. Okay. Here's another differential equation, and do you see how if I follow the same pattern that I used here, I'm going to wind up with y is equal to p times e to the 8x. If I went through that exact same process, I'd get to y is equal to y is equal to p times e to the 8x. And again, if I have an initial condition, if I plug in 0 for x and 10 for y, I get p is equal to 10. So y is equal to 10 e to the 8x. If you don't believe me, go through these steps again and make sure that it works. But as long as I have my differential equation is a constant times y, then I know that it's going to wind up following that same pattern. And so if I have a differential equation that's written this way, as long as my derivative is a constant times y, or another way of saying this, as long as the derivative is directly proportional to y, so some constant times y, then I know immediately, without doing all of the steps, I know immediately that y is equal to p e to the kx. And if my initial condition is 0, p, I can solve for that p really quickly. So this is the differential equation that gives us that PERT formula. I've just used the letter K instead of an R for rate. And that follows from separable differential equations. So here's that kind of formally. If your derivative is a constant times your function, then your function is y equals p e to the kt. The initial amount is p, and it's sometimes called y sub 0. So for example, if I want to solve this differential equation without separating out the variables, I know that v is equal to p times e to the 1/2 t. And I don't know what the initial amount is, but if I knew what the initial amount was, I could fill that in as well. All right, the second part of this unit is Newton's law of cooling. And Newton's law of cooling says that the rate of change of the temperature with respect to time, so big T is temp and little t is time, is going to equal a constant times the difference in the room temperature and the temperature of the object. Okay, so T is the temperature of the object and T sub R is the temperature of the room. Okay, so I have a rate of change is directly proportional to a difference. So I think this is going to be exponential, but let's go through the process of filling it in. Okay, so a body's found at 9 a.m. in a 68-degree room. So I'm going to replace T sub R with 68 degrees. The body is 90.3 degrees. An hour later, it is 89 degrees. When did the murder occur? So we're going to go ahead and separate out the variables for our differential equation. So d sub t dt is equal to k times t minus 68. I'm going to separate out my variables. So dt over t minus 68 is equal to k dt. So natural log of t minus 68 is equal to kt plus c. This time I don't need absolute value bars because I know that t minus 68 is going to be greater than 0 because I don't think the body temperature is ever going to get colder than the room. So if I exponentiate now, I have t minus 68 is equal to, and maybe you recognize this already as p e to the kt. And then my temperature is equal to p e to the kt plus 68, but I have a whole bunch of variables. I don't know what my initial temperature is, and I don't know what my K is. So the way I'm going to figure that out is I'm going to use this given information. So T equals 0, I'm going to call the time the 9 a.m. time. And at that time, the temperature is 90.3 degrees. So I'm going to fill that information in, and I'm going to use that to figure out what P is. So 90.3 is equal to P e to the kt, except T is 0, so P times 0, P to the 0, plus 68, which means P is equal to 22.3. And then the other piece of information I have is an hour later, so T equals 1, the temperature is 89 degrees. So I'm going to fill in T equals 1. So I have 89 is equal to 22.3 e to the k times 1 plus 68. So 21 equals 22.3 e to the k. So k is equal to natural log of 21 divided by 22.3. That's a number that I can find on my calculator if I have one. So I'm going to just go ahead and pretend that I'm storing that on my calculator. So here's my calculator. I'm going to take natural log of 21 divided by 22.3. And then the way I store that is I hit Control, var, and then I type K. And now that whole decimal is stored on my calculator as a value I can use later. Now I want to know when the murder occurred. I'm going to assume that the body was healthy when it was killed, so I'm going to assume that its temperature was 98.6 at the time of death. So I'm going to figure out what the time of death is, and the way I'm going to do that is I'm going to say 98.6 is equal to 22.3 e to the k, and even though I'm writing a k, it's a number that I know, it's just that ugly decimal, plus 68. So I'll move the 68 over, so I have 30.6, oops, divided by 22.3 is equal to e to the kt, and again, I know what k is, I just need to use that. So if I take the natural log of both sides, I have natural log of 30.6 divided by 22.3, and that's something I can easily find on my calculator. Divide that by k, and that's going to give me the time of death. So if I type that on my calculator, divide that by k, and so I get that the body was killed, oops, t equals negative 5.267. And if you really want to be a detective, you would know that that's about 3:44 a.m. is when the body was killed. You don't have to memorize Newton's law of cooling. All of the steps of solving that differential equation should make sense to you. So if it, and you should be able to solve a similar problem given information about room temperature and something cooling if you're given that differential equation. So these are the notes for today. It is I would try the population growth and the puppy growth problems on the back of the sheet, and let me know in class tomorrow what questions you have.